Hello, in today's video we are going to be talking about fluids in motion, and after watching this video you should be able to understand and apply Pascal's principles, get a general understanding on how hydraulic lifts work, and be able to calculate the pressure by a fluid on an object. Alright, so let's get right into what we're doing here. Pascal's principle is all about pressure in a fluid, and I don't know if any of you guys have ever dove to the deep end of a pool, but if you do and you touch the bottom of the pool, you will feel pressure on your ears, right? It feels like your ears are being squeezed, and that is due to the weight of the water above your head. And so Blaise Pascal was the first guy to note this, and he noted that actually the shape of the fluid has absolutely nothing to do with the pressure applied by the fluid. Instead, it just has to do with depth. And so what that's basically saying is, you know, if I have just a normal glass here with water in it, or if I have like a really cool looking glass that's kind of curved shape, as long as the depth and the amount of water that's above your head is the same, the pressure is actually constant. So I mean, I can make a glass that looks like a triangle, I could make a glass that looks like a diamond. It doesn't matter as long as the depth that you're at below the fluid is constant, the pressure will stay the same. The shape has nothing to do with it, which is kind of cool. I wouldn't actually think that would be the case. He also found that the pressure applied to a fluid is constant, and it's spread throughout the entire fluid. So my example is like, if any of you guys brush your teeth, which I hope you do, if you get a tube of toothpaste, and if I can draw a tube of toothpaste here, and then I wish I was a good artist, but that's supposed to be a tube of toothpaste. If you squeeze the toothpaste down on this end, you know that the pressure is applied to all the toothpaste in this tube, and it causes it to come out, right? And so that's basically Pascal's principle. Every time you brush your teeth and squeeze some toothpaste out, you are applying Pascal's principle. So let's take another example about Pascal's principle, and this is kind of my balloon example, and I try to use the term work in equals work out. Basically, the pressure that you put in is the pressure that you're going to get out. So let's take a look at, say, a balloon, and I need to change my pen color so you guys can actually see it. That would be good. Let's see here, what would be cool? Magenta sounds nice. So let's say I have a balloon, and here's my balloon right here. And I'm going to say, like, this part of the balloon is metal, which makes not a lot of sense because there aren't really many metal balloons. But this is a rigid structure here. You can't change the size of it, okay? And let's say I put some sort of like metal plate in the balloon, and with like a plunger on it that I can push down on this metal plate. And this balloon is filled with water. Okay, this is all water in this balloon. And I push down on the metal plate. What ends up happening is the pressure applied by the metal plate is spread throughout the entire balloon, and the balloon actually expands outward. And that's Pascal's principle, basically, is that the pressure applied at this little point right here is equally distributed throughout the entire balloon. The whole balloon feels that pressure. The formula for pressure is P equals F over A. P being in pascals, so that's where it came from, force being in newtons, and area usually being in meters squared. And this can be applied to, say, a hydraulic lift. And I'm going to do another example with this shortly, but if I draw a hydraulic lift here, let's say I draw something like this. All right. Basically, a hydraulic lift has like two little metal plates in it, and then there's a fluid in here, okay, spread throughout the entire thing. Okay. Basically, if I push down with, say, a pressure here of P1, we'll call it, this side over here, this lift over here, experiences the same pressure. It'd be a pressure of P2. Okay, so again, kind of like this water balloon, if I push down with a pressure of 10 pascals as P1, P2 is also going to feel 10 pascals of pressure. All right, so we can kind of write this as P1 equals P2. All right, so let's take a look at the equation for hydraulic lifts, and here's kind of this picture that I was trying to draw for you before. the force applied here and the force over there, those aren't actually going to be the same. You'll notice the arrow here on F2 is longer than the arrow on F1. And we're going to take a look at this because this is actually a simple machine. You gain mechanical advantage with hydraulic lifts. And this is kind of like what they do with your car. If you bring your car into the repair shop and they lift your car up on one of those lifts, same idea here. But this equation will come in handy. So I recommend writing that down. So F2 equals F1 times A2 over A1. And that doesn't make maybe a ton of sense right now, but if you kind of think about P equals FA, and we're looking for the force, another way of writing that equation is F equals PA, right? So if we're comparing these two lifts, we're just basically melding this equation into this right here. Okay, and we'll practice this more in class. But for right now, just take my word for it that F2 equals F1 times A2 over A1. Okay, and we're going to do an example problem with this right now. Okay. So if we draw our hydraulic lift, and let me just get my pen to the right color. If we draw a hydraulic lift and we practice a hydraulic lift problem, I'll draw my lift here. And again, there's a metal plunger on either side, or a lift, I guess, on either side, and there's a fluid in here, so keep that in mind. All right. A few things that I'm willing to tell you guys is that the formula for pressure equals F over A. So keep that in mind. So let's say I apply a pressure of 10 pascals on this side. Okay, and we will say that the area of the left-hand side, A1, is 2 meters squared. Right. So the area on this side is 2 meters squared. I'm applying a pressure of 10 pascals. What pressure then is applied on the right-hand side? Okay, so what is my pressure over here? What is this pressure up? And the answer actually is, according to Pascal's principle, it's 10. Right? It's 10 pascals because remember the pressure applied in one area of a fluid is going to equal the pressure everywhere in the fluid. So it's 10 pascals up. And this side we'll say is about double the size of the left-hand side. I don't know for certain if that's correct, but we'll say that A2 has an area of 4 meters squared. Okay, so my question is, what is the force applied on the right-hand side compared to the force on the left-hand side? So if we start to kind of just take a look at deriving that equation, the hydraulic lift equation, remember P1, we'll call this P1 over here, and this we'll call P2. P1 equals P2, okay? So what I can actually do is I can set this formula equal to one another. I can say F1 is over A1 equals F2 over A2. And basically what I'm saying is this left-hand side of the equation here is relating to this part of the lift, and the right-hand side of the equation is related to that side of the lift. Okay, because P1 equals P2. The pressure on the left equals the pressure on the right. All right. So my first question to figure out the F2 is I would need to get F2 by itself, and so that becomes F2 equals F1 times A2 over A1. Okay, and that's where the formula in the previous slide came from. Okay. Before I can use this formula, though, I need to figure out F1. Okay, I need to figure out the force on the left-hand side, and that's not too bad. It's, P equals F over A. So all I have to do is, A is 2, F I want to know, and P is 10. So cross multiply. I have a force on the left, F1 equals 20 newtons. Okay. So I can now plug that into this equation, and I know my other things, and I can find out F2. Okay, so I'm going to do that right up here. F2 equals F1, which is 20 newtons, times the area of 2, which is 4 meters squared, divided by the area of 1, which is 2 meters squared. All right, and so if my math is right, 20 times 4 is 80, divided by 2 is 40, and so F2 would equal 40 newtons. Right? And that kind of makes sense. If the area is double, the pressure is going to double. And basically, this is a mechanical advantage of about 2, right? So that's how this is a simple machine. If I can push with a force here of 20 newtons, and I get a force of 40 newtons out on the other side. And this is how car lifts work. You know, if you go to a car repair shop and they put your car on the lift, to lift your car up, which is relatively heavy, you use something like this, a hydraulic lift, to make that happen. All right. So now what we're going to do is we're going to start talking about the pressure on a fluid, or pressure on an object in a fluid. Okay, and so again, if you dive to the deep end of the pool and you're way at the bottom, you touch the bottom of the pool, you can feel that pressure on you, and that pressure is the result of the weight of the water above you. Okay, and this is kind of a key thing to note. The pressure on an object is equal in all directions. Pressure doesn't just push down, it doesn't just push up or to the right or to the left, it's equal in all directions, okay? And the pressure on a fluid can be determined by this formula right here, and there's some new things that we need to talk about. What is all this junk here, right? The P in this is pressure, so big P is pressure, which is a Pascal. Okay? It looks like a P, but they actually call this rho, and a lot of times they put a little curl on it. But rho is actually the density of a fluid, whatever you're in. Right? And one number that's kind of good to know is that the density of water is 1,000 kilograms per meter cubed. Okay, that's kind of a good number just to know, because there's a lot of problems that deal with water, and so if you can just know the density of water is 1,000 kilograms per meter cubed, that's not a bad thing. And then H is the height. H equals the height of the object, or the depth of the object. And then G, well, G is what we've been using G for all year long. That is the gravity. So the pressure of a fluid, say on the moon, is going to be different than the pressure of the fluid on Earth, okay, because Earth has a stronger gravitational field than, say, the moon does. Okay, so let's do an example problem with this. That might make it make a little bit more sense. Just get my notes here real quickly. So let's say you've got a cylinder, and the cylinder is filled with a fluid, say up to here. Okay, so we'll call it water just to keep it simple. Okay, and let's say I put like a thin metal plate here at some depth, okay, which is usually represented by an H. Okay, so you have a thin metal plate at some depth, and maybe I'll change the color so that we can kind of keep that idea going here. So this is the metal plate, okay, thin metal plate at some depth, and I'm wondering what the pressure is on that metal plate. Okay, and so let's say H is, well, let's say 2 meters. 2 meters. Okay, it's at a depth of 2 meters in some water. Okay, and I want to know what is the pressure on that plate. That is the question. Well, remember, pressure equals rho hg. Okay, and so basically, it's just kind of plugging numbers in. I know rho is 1,000 kilograms per meter cubed, times h, which is 2 meters, times g, which on Earth is 9.8 meters per second squared. Okay? And if you do those calculations, it would be, let's see here, 2,000, I should just probably get a calculator. So let's see here, we have 2,000 times 9.8. We get 19,000, so we have a pressure of 19,600 what? Pascals. And that seems like a huge number, but it's actually not very much, not that big. This is considerably less than like 1 atmosphere of pressure at sea level, so that the weight of the air on you is more than this. But that's basically what's happening here. Now, in the next video, we're going to use this in a little bit more depth here. But this is basically how you find out the pressure of an object in a fluid. And as I mentioned in the previous slide, just one other little side note here: the pressure is equal in all directions. So it's not just pushing down or it's not just pushing up. It's equal in all directions, from the sides, any direction you want. the pressure is equal. And how do we know this? Well, the reason why we know this is because this little metal plate or whatever is not moving. There is no net force. And since there's no net force, there is no movement. If there was a bigger pressure coming from the bottom pushing up, then the metal plate would move up. Or if there's a bigger pressure pushing down, then the metal plate would move down because a net force causes movement. But since there is no net force, the plate just stays in its one spot at a constant location, at a constant H. Okay, we will see you guys in the next video. Until next time.